Hello, quick video on differentials of natural exponents and logs. In previous videos we found the value of E, Euler's number, and as a result we have two functions based on that E value. First one is the exponent form, the e to the power x, fx is e to the power x, and then we have the inverse function, the natural log version of the form, so that's the inverse function of e to the x. So that's how we find what that exponent would be. And what we're going to do today is look at the differentials of these functions, and also we'll touch on their integrals as well, which are useful. Okay, in the previous video we investigated the curve y equals a to the x, the exponent, the power version of this, and we looked at its gradient, and we actually chose the value of e such that we get the property that we're interested in, that if our function, if we drew a graph of y equals e to the x, we would find that the gradient of e to the x is that value, the value of the function I, the value of y at that point. So if we have a quick look on Geogebra here, here's the curve of y equals e to the x. Here's a point 1 at 1, at this point x equals 1 at this point, and we can see that the y value here is about 2.72, and here is a gradient triangle for the tangent that shows the gradient at this point is 2.72. If I move along, say to let's get to 1.5, my y value is now 4.48 and my gradient is 4.48, and if I go up to x equals 2, then my y value is 2.39 and my gradient is 2.39. So that gives us a pretty straightforward demonstration that if we've got a function of the y value and y is e to the x, then the gradient at that point is also e to the x, and that's why we chose e. It also has useful phenomenon results when we combine it with the chain rule. So if we look at y equals e to the power kx and we differentiate that, we find that the gradient of the curve is k times e to the kx, and we use that in lots of physical phenomena like rates of cooling, radioactive decay, population growth. In finance you have interest or depreciation coming out of that. And of course there's a pretty simple corollary here, that when we look at the integral, that if the differential is e to the x, then the integral of e to the x will also be e to the x, and if we integrate it e to the kx, we're going to end up with e to the x over k. So that again is quite useful and what we're looking to do. Next step is for us to look at the inverse function of the log function, and this proves to have a very useful relationship to its values. And again, best to look at this by looking at a curve, the curve itself. So here we have the blue line on the GeoGebra now is the natural log function ln of x, and again I've got a point here. This point's going to be point B here, which at present is x equals 1, and at this point the gradient, we can see here in the gradient triangle, is 1. If I move that up now so that the value is x equals 2, we find that the gradient is now a half, and if I go to x equals 3, the gradient is now a third. So can you see that what we're seeing is the gradient is the reciprocal of the x value, yeah, 1 over x. So here x equals 4 now, so 1 over x is a quarter or 0.25, and if x equals 5, and then now the gradient is 1 over 5, 1 over x is 0.2. So that's quite a nice simple relationship, isn't it? So for the function y equals the log of x, then the differential of log of x is 1 over x. Now that's actually quite useful for solving another problem that we had. In the past we've not been able to integrate 1 over x because our normal algorithm doesn't work for it. So if it's true that the differential of log of x is 1 over x, then if we go in the inverse direction, then the integral of 1 over x must be the log of x. And actually, we have to look at the modulus as well. That's okay on the positive side, but it also works on the negative side if we add the modulus lines. So not only have we found out what the differential of log of x is, we've actually found the integral of 1 over x, which is extremely useful. So in summary, the natural exponent form is a function is e to the x, and the inverse function is the natural log of x. The differential of e to the x is also e to the x, and as a result, therefore, the integral of e to the x is e to the x. And looking at the log form here function, the differential of the log function is 1 over x, and useful to bear in mind that the integral of 1 over x is log of x, and log of modulus of x. So I hope that's of use to you.